Hello, welcome to Electronics Education. I'm Vincent Chang. In this lecture, we are going to solve a case to investigate the stability of feedback for a non-inverting operational amplifier. Non-inverting operational amplifier. Stability of non-inverting op amp. Introduction. So before we can investigate the stability of this circuit, I want to make sure you understand, you have all the knowledge. You already have the solid foundation on all the detail. Otherwise, you will get stuck in some of the nitty-gritty detail when you investigate the circuit, the stability of this circuit. So let's quickly review the feedback topologies. Right? Here's the ideal feedback structure. On the left-hand side, you have mixing. On the right-hand side, you have sampling. Now, on the left-hand side, there are two ways of mixing. Series mixing for the voltage signal and shunt mixing for current signal. On the right-hand side, also two ways of sampling. Shunt sampling for voltage sampling and series sampling for current sampling. So four combination, four topologies: series shunt, shunt series, series feedback, and shunt feedback. So let's focus on the first case, the series shunt feedback. So it's the voltage input, voltage output. The corresponding associated, the amplifier, the essence is a voltage amplifier, Now, here's an ideal non-inverting operational amplifier. So based on what you learned before, through other video lecture, then what is the if the op amp is ideal, what is the closed loop gain here? So in ideal case, that you can just apply the virtual short circuit between the inverting terminal and the non-inverting terminal, right? So the non-inverting terminal voltage, maybe you have to put down in this. Let me just use the analysis by inspection. For the non-inverting terminal voltage is VI. For the inverting terminal voltage is the divider from the output. So VO times a ratio. What ratio? R1 divided by R1 plus R2. Then equate these two voltage together. The negative voltage, the inverting terminal voltage equals the positive terminal voltage, give us this answer. All right? So here's the closed loop gain is 1 plus R2 over R1. So this is the ideal non-inverting op amp. But you can also look at this from the feedback perspective. Let me ask you, what feedback topology is this circuit? What feedback topology is this circuit? What type of mixing and what types of sampling? What types of mixing and what types of sampling? What kinds of mixing at the input side and what kinds of sampling on the output side? So make sure you can identify the circuit I just mentioned, a non-inverting amplifier. So I want you to associate the circuit with the feedback topology. Just redraw the circuit on your note and think about this for a few minutes. So what feedback topology is this non-inverting amplifier is? All right. So I'm back. So what feedback topology is this non-inverting amplifier is? These two is kind of equivalent, right? Not exactly equivalent to each other, because the right-hand side is the special case of the left-hand side. And what special case? Let me repeat that. The right-hand side circuit is a special case of the left-hand side circuit. Under what condition? Under what condition? Under when Rs equals 0, zero source resistance, and the infinite load resistance, and also the operational amplifiers is ideal. All right? So it's the special case of the left-hand side. And then these two, can you relate these two to each other? So it's a series mixing, right? And then shunt sampling. It's a series mixing. Look at the left-hand side. It's a series mixing, and then it's the shunt sampling. So the non-inverting amplifier on the left-hand side can be identified as a series shunt feedback. A series shunt feedback. So the answer to my question is series shunt feedback. Series mixing and shunt sampling. Maybe you can just turn upside down. Just turn 180 degrees. So now Vs is on the top, the non-inverting input, and the feedback network. This might be easier for you, right? Series mixing on the input side and shunt sampling at the output side. Next question. So it's the series shunt feedback. So what about beta? What about beta? How to determine beta? How to determine beta? In the analysis, in the upcoming lecture, we can just assume infinite differential input resistance for the op amp, and also zero output resistance for the op amp. Infinite resistance and zero output resistance. So what is the beta? What is the beta? So let's pull a series feedback structure on the right-hand side. How to determine the beta of a series feedback? How to determine the beta of a series shunt feedback? A series shunt feedback. The beta is defined by a parameter called H12, which is defined as V1 on the left-hand side and V2 on the upper side. So it's the reverse transmission. The left-hand side voltage divided by the right-hand side voltage under what condition? I1 equals 0. So let me repeat that. For the feedback network, you can just send in a testing voltage from the right-hand side, from the output side, V2, and then try to measure the result, the voltage on the left-hand side, V1. So V1 divided by V2, and the set I1 is 0. Set I1 is 0. All right? So V1 divided by V2 when I1 is set to 0. This is the definition of beta for series shunt feedback. For series shunt feedback. So let's look at this again. When V1, look at the left-hand side, divided by V2, and you break the I1. You break the I1. So when I1 is 0, this represents the break, the open circuit. You open the input loop. Then the R1 and the R2 and R1 share the same current divider, right? So R1 divided by R1 plus R2. So here's the beta for this non-inverting amplifier, all right? So can you relate these two to each other? Can you relate these two together? The ideal, the closed loop gain. So closed loop gain is the 1 over beta, right? Beautiful. Remember this? Because in many cases, the loop gain is greater than 1. So when loop gain is greater than 1, then what? Then the closed loop gain will be solely determined by beta. It's 1 over beta. So I've almost come to the end of the lecture. Here's the takeaway. Closed loop gain. 1 plus R2 over R1. Then series shunt. Then how to determine beta? So number 1, closed loop gain. Starting with closed loop gain, and then I talk about series shunt feedback, series mixing, and shunt sampling. I ask you which feedback topology this circuit belongs to. So number 3, how to determine the beta. And the last one, the relationship between these two. The closed loop gain is 1 over beta. So we have come to the end of the lecture. I hope you learned something from this lecture as a solid foundation when we move forward to investigate the stability of the feedback for this non-inverting amplifier. I look forward to see you in the next video lecture. Thanks for watching.